we are going to go into the rotational inertia, but the calculus. Now, I'm here to tell you, the calculus part is actually the easy part. And what I'm going to try to do to the best of my ability is explain how the calculus and the physics are related. So let's begin. By the end of this video, okay, what we're trying to do is actually derive this formula right here. Okay, so we are going to create a rod that is rotating about the axis. So imagine that you have this is my rod, and my rotation axis is right here at the end, and we're trying to rotate it around that endpoint there. Okay, so let's begin. The very first thing that I want us to do is to remind yourselves that if we have a point particle, okay, so a point particle, there we go, point particle that is rotating, okay, so for a point particle that's rotating, so this is my axis of rotation, and all the way out here, we have a point particle that's able to rotate in either direction. We say that the rotational inertia is I is equal to mr squared. Now, this is actually where the journey begins for the calculus work. Now, a point particle is like a very tiny bit of mass that is at a location r away. But what if we have another tiny bit of mass that's a little bit closer? And then another one that's a little bit closer, 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 and closer. And hopefully by now you're starting to see a trend here. This is my axis of rotation, and we keep on adding these tiny bits of mass. What you end up with, right, and all these tiny bits of masses are lined up, you get a solid object, and that solid object is called a rod. That's right. So a rod, we have to view a rod is just point particles all lined up. All right. So that's the big main idea behind this, and let's try to get right into it. All right. So the idea here is if we are taking tiny bits of something. So I'm just going to actually sketch a rod, like a physical rod, not those tiny point particles. And we'll just say the axis of rotation is right along here. That's my axis of rotation. So the idea of calculus, right, is if you're trying to get tiny little bits of pieces of a object, right? So the idea is if we were to take a chunk of this rod right there, okay? So that chunk of the rod, so if I were to zoom in on that chunk on this area here, right? If I were to zoom in there, this is my zoomed in image right here. This is what we're going to see. We're going to see, so let's see here, if I were to recreate it, right? So that's the left line here, and this is the right line there, and this is the rest of the rod here, and the rest of the rod is over there, like so. All right. So let's go into the basic ideas of calculus. So what these tiny chunks are saying is if you go from the axis of rotation, which is over here, all the way to the first vertical line there, all right, what we're getting here is, let's say, R1. And we can do the same from here, axis of rotation, all the way out here to the other line. So all the way out here, this is R2. So what you're seeing is a difference is in R1 and in R2. So another way of writing this is difference in R, which is R2 minus R1. All right. Now in calculus, that triangle, right, we just replace it with the letter D. And so going from this point here to this point here, we're going to call that dr. And so the idea that we're trying to really investigate is if you were to take a look at from R1 to R2, and we look at this chunk of the rod, we can say that that chunk of a rod has a tiny bit of mass that makes up the rod. And we say that the tiny bit of mass is what we call dm. All right. So here we just went over how we came up with dr, and when we are looking at tiny bits of dr, we are looking at the tiny chunks of the rod, which is dm. All right. So what that brings us is if we are looking at tiny bits of mass and tiny bits of r, and just as a side reminder, inertia is mr squared. you can see how we can take a look at tiny bits of mass and tiny bits of r to come up with the whole inertia. So the formula that I want us to start off with is the integral of di. So what this is saying is we're going to be looking at all the tiny little bits of rotational inertia. Now this actually goes back to the idea of lining up those particles, right? So this di is if you were to get the rotational inertia of one particle and add it to another particle and add it to another particle, right? And add it to another particle. So that's all those di's added up, right? And on this side, what we're looking at is dm and r squared. And that dm is there because we want to be taking a look at the tiny bits of mass and how the location of the radius is affecting those tiny bits of mass. So that's actually our starting line. So let's start off there. Now, let's take a look at there should be an integral symbol there, the ideas of calculus and the rules of calculus, all right? So we've learned that whatever is after this d, right? So in this case, this is the variable m. Those, like, that's what tells you your bounds, right? Your upper and your lower bounds. But what we actually want to be doing is we want to be going across from r of 0 all the way out there, which we're going to say the total length is just L. Okay, so we want to be seeing how the inertia is changing as you go from one point of the rod all the way to the other point. What that means is we can't take a look at this in terms of mass, but rather that dm actually needs to be dr. All right. So what this means, let's actually write that down. dm needs to be dr. So what this means here is that we need to do a substitution. Okay. Now, for the record, right, why we need to change dm to dr is because we are seeing how the I adds up as we increase the r, right? So back to the idea, if this is your axis of rotation and we have a point particle here, right? This point particle has a I. I'm going to call this I1. If we put a point particle right next to it, this here has I2, point particle right there. This is I3. So the idea of this integral of di is, hey, you take all of those point particles from the axis of rotation where r is equal to 0 all the way up here to r equals L, and that gives you the total inertia of this rod. All right, so that's why we need to change the dm to dr, because we are looking at how the inertia changes or how the inertia accumulates as you increase the rod. All right, so that was a lot of talking, and let's actually get down to the calculus. So that's the difficult physics idea behind it. We're trying to give this formula and this calculus some meaning. Okay, so before we continue, here's a little side note. All right, so this is a side note. When we do these problems, you'll see different ratios, okay? And the ratios that we're looking at is the density ratios. So we know density, for physics class, there are three types of densities that you'll be looking at. The first one is, so I'm going to write the Greek letter here. This is rho, and rho gives us mass over volume, okay, or m over v, and whatever that volume might be. So it could be like a cylinder, it could be a sphere, right? It could be, all sorts of different things. The other one is sigma, which we draw like that, and this is mass over area. So imagine, like, I don't know, let's say you have like a potato chip, and there's just some parts of that potato chip that have a little bit of extra potato, so it has the or like extra salt or extra seasoning. So the density of that area might be different than other parts of the density. Okay, and the other one is lambda. Lambda is mass per length and that's the one that we're looking at today. All right. So you don't need to have these memorized, right? The formula, or excuse me, the problem will tell you which one to use, but you need to understand that it doesn't matter if you're given rho, sigma, or lambda. You just need to know that it is a density, and density is a ratio. Okay. All right. So let me just fill this out here. And just so you know, we're going to be using the length density ratio formula for our problem. Okay, so back to here. Actually, I'm going to just rewrite that so that it looks a little bit cleaner. Let me get r squared dm. Okay, so we left off with saying we need to perform a substitution for that dm, and that substitution sub comes from density. Okay, so we know that lambda is equal to mass divided by length. I'm going to put that as a capital L actually. Mass over, no, mass per length, which in this case would be like a R. Uh, that will be different. Excuse me, length. Uh, and if we are looking at this as a ratio, if this m represents the total mass and this L represents the total length, if we're looking at tiny bits of that rod, we will get tiny bits of mass over tiny bits of length, which I'm going to replace that L with the R. So a little side note here, side note, uh, for Mr. Lee's class and a lot of physics, capital letters, capital variables are constants. Okay, so you'll see here that I use the capital letter L, and that's to represent the physical length of the rod, which is a constant, right? Like the length of the rod's not changing, and this M here, like that would be a capital M, and the capital M is the actual mass of that rod. Compared to over here, it's kind of hard. Well, let me write a bit better. There we go. All right, so let's make this capital M, and this is a lowercase m. And so for physics and a lot of times for math, we use the lowercase letters to represent a variable. So this dm is a tiny bit of this capital M, okay? And this r is a tiny length of this rod, all right? Okay, so taking a look here, we see, so there's a lot of different ways that you could rearrange this formula to get what you need, right? So for this is like a side example, but we can say, hey, this is equal to dm over dr, right? And so depending on the problem, right, the problem can say, all right, so you gotta substitute in this, right? Or for our problem here, we're going to be using this relationship, okay, where dm is equal to capital M over L dr. So the big idea here is this this density relationship. You can rearrange it for the problem that you need. And I'm here to tell you the relationship that we're going to be using will be this one. So if we substitute in that dm, we will get the following: M over L dr. All right, so let's do a quick calculus slash physics check. The whole purpose of substituting in this dm with this ml over dr, right? So I just highlighted what we just substitute. In class, you'll see me usually perform my substitution with parentheses so you can see exactly what changed, is so that we can find the rotational inertia as we have a change in length, not a change in mass. So we change that dm, which is a changing of mass, to what we want, which is a change of length. All right, so now let's talk about our bounds. Our lower bound is where we're starting from, or our axis of rotation starts, which is r of 0. And our final length is the actual physical length of the rod itself, which is r is equal to capital L. So, and like I promised, the actual calculus of this is easy. Now I'm just going to rewrite it below so that we can talk about this. Okay, I'm going to rearrange my formulas like so. Now, it's important for us to identify what are my constants. And that's the whole reason why I had this talk over here about what I use as capital letters and what are lowercase letters. Because just like in calculus, if it's a constant, you can actually pull it out of the integral, pull it out to the left or pull it out to the front. So this is the mass of the rod, which is a constant, and this is the length of the rod, which is a constant. So I'm going to pull those out to the front. So this scary looking integral actually becomes a lot less scary because, hey, look, all we're doing is we're integrating r squared with respect to dr. So if we're integrating r squared with respect to dr, we will get capital M over L, okay? And then we will get 1/3 r cubed, where our bounds are from 0 to L. And by the way, the left-hand side, right, if we're integrating the I, this is just giving us the rotational inertia I, right? So from here, I'm going to perform my substitutions, okay? For the sake of the length of this video, I'm gonna skip ahead. I'm gonna skip substituting in that 0 there. But what we get is 1/3 L cubed. Right? I don't want to do any canceling out just yet, so that you can see here we have M over capital L times 1/3 times L cubed, and whoa, we will get 1/3 M L squared if you perform your algebra correctly. And if you remember from the very beginning of the video, I said we are to derive the rotational inertia of a rod, which is 1/3 ml squared, and look at that, 1/3 ml squared. Isn't that cool? All right, so another reason why we have to perform calculus for rotational inertia is if the problem tells you. So by the way, that example was for a uniform density rod, which means that like the rod is made of the same material. There's no changes, no fluctuations at all of that rod. But what if you have a rod that changes in density as it goes away from the axis of rotation? I don't know, like let's see, I think in my previous video I called it like a corn dog, right? So different parts of the object is made out of different things, so the density changes. So what about what if you have, let's say, a rod kind of looks like this, right? Almost like, I know, like in the summer growing up, one of my favorite things was like I forgot what they were called, but it was an ice cream where it was like the waffle cone, and there was the ice cream, and there were peanuts, and there were chocolate. So essentially, different parts of the object were made of different things, right? And so here the density is, so this is a non-uniform density. Okay, so this is non-uniform density, and for problems like this, they'll tell you. Okay, they'll give you a function. And so for in this problem, they'll say, hey, let's say lambda is, I don't know, what did I write here? Let's say lambda is equal to bx, right, for this weird looking shape. And the length of this rod, we'll just make it easier ourselves. We'll say the length of this rod is L, where x is a variable, okay, and that represents like the length. And this b, I'm going to highlight it so it kind of stands out. B is a constant, right? And that constant could be like any number. It could be like 100, it could be 0.2, right? It doesn't matter. It could be any number. So how do you solve a problem like this? Well, you solve it the exact same way, right? So you solve it by having your first line. So we're going to say di is equal to integral of r squared dm. And yes, you should always start off with the actual rotational inertia formula. So here, this is the regular version, right? mr squared. So this is like line 1 technically. And if we're like, but we're about to do calculus, so this is now your line 1. So don't skip this step. Always have it there because it tells exactly what's happening. All right, so if you remember, so this is, so step 1 is have line 1. Okay, step 2, sub, right? You got to perform your substitution. I always like to do my substitution work off on the side, so I'll do that over here, right? So we know that lambda is equal to bx, but we also know that lambda is also equal to, well, dm over, well, here they use x, so I'll just keep on using x, so dm over dx, right? So mass over length. Okay, and so from here, right, we need to figure out what can I substitute in to create my substitution that can go into that formula. So I'm going to show you two different ways, right? So the first thing I want to show you is dm is equal to lambda dx, right? So I'm going to highlight that. Boom, boom, boom. And the other one, watch this, same exact thing. I'm just going to replace my lambda with the formula the problem gives me, which is b bx dx. All right, so I'm going to show you both of those lines. So we already know that this left-hand side, this is I. So here, r squared lambda dx. Now, me personally, I like to show all of my steps, okay? Especially if you're trying to help out others, like they need to see where everything is coming from. Bx dx here. Okay, so at this point, I'm going to do a little side note, okay? The function uses x instead of r, right? So the function uses x instead of r, so I'm going to replace it in the next line. So this is x squared bx dx, right? You have that power. You're in charge of your calculus. You can do whatever that is within the rules of math here. And at this point, you're almost done. Okay, well, first you need to set the bounds. We said our initial position bound will be 0, and our final position will be L. Okay, and so look here, we get 0 to L. I'm going to just clean this up. This is bx cubed dx, and at this point, you just got to ask yourself, right? So if this is step 1, have line 1. Step 2, perform your subs. And I'm going to say step 3, make all variables communicate with each other. So that means that we replace the R with the X. And the final step is, well, not the final step, pull out constants, right? Pull out your constants, and then you can actually integrate at the end. All right, so I'm gonna do sets 4 and 5. So here, right, we start off with the problem saying that the b is a constant. It just represents the number. Gonna pull that out. B 0L x cubed dx, and you're thinking, wait a minute, I can perform that integral, and I'm pretty sure you can. I'm going to show all the steps just in case. 0 to L, right? And then we get a final integral, a final answer of B. So quarter B L to the fourth is my rotational inertia. And that's how you do it if you have. So by the way, this, like the steps and all of that is the same, whether it's a uniform or a non-uniform. But I just showed you here, this is how you would do it if it's non-uniform. They give you a function for the rotational inertia. All right, see you next time. Bye-bye.